Moving on to chapter 5, we talked about the first few sections of chapter 4 before Christmas break. Took a quiz before Christmas break over those sections. Then we finished chapter 4 when we came back from break, and we took a quiz yesterday. So I feel like we've covered chapter 4 enough, and we're going to move on to chapter 5. Okay? Chapter 5 is all about solving systems of equations. There's multiple methods to solve systems of equations. So today, we're going to look at solving systems of linear equations by graphing. Solving systems of linear equations by graphing. So let's first understand what a system of linear equations is. It is a set of two or more linear equations in the same variables. So you have two or more equations together in a group, and they have the same variables. That's what a system of equations is. An example of that is shown below. X plus y equals 7, 2x minus 3y equals negative 11. How many equations do I have there? How many equations do I have there? Two. Do they have the same variables? Yes. X and y, right? Both have x, they both have y. So this is a system of linear equations. A solution of a system of linear equations in two variables is an ordered pair that is a solution of each equation in the system. So let's think back to chapter 3, I believe, when we kind of graphed a little bit. If I had an ordered pair and I plugged it into my equation and it gave me a true statement, it was a solution to that equation. Right? Plug in the x value for x, the y value in for y. If it gives me a true statement, it's a solution to that equation. Do you guys remember that? Somewhat, at least, hopefully. So, kind of the same concept here. A solution of a system of linear equations in two variables is an ordered pair that is a solution of each equation in the system. So, if the ordered pair is a solution to neither of my equations, it's not a solution to my system. If the ordered pair is only a solution to one of my equations, it's still not a solution to the whole system. It has to make both equations true in order for it to be a solution to the system as a whole. Okay, and we'll look at some examples of that here in a second. For an ordered pair to be a solution, it's got to make both equations true. That's essentially what that's saying. Any questions about what a system of linear equations is or what a solution of a system of linear equations is? Yes? Yeah, it's got to make both equations true for it to be a solution to the whole system. It can be a solution to one of my equations, but not a solution to the system as a whole unless it fits both equations. I want y'all to think about this. If I've got a line, any ordered pair on that line is a solution of that equation that graphed that line. Do you guys agree with that? So, here in a second, keep that in mind whenever we're talking about graphing. Can I move on? Example 1, tell whether the ordered pair is a solution of the system of linear equations. So each example gives me an ordered pair and a system of equations. How do I know if an ordered pair is a solution of a system of equations?
Yeah, it makes both equations.
Makes both equations true. So how do you think I'm going to check this? Plug it in for x and y into both equations. Because I got to make sure it works for both equations. So, first equation, x plus y equals 7. What am I replacing x with?
2.
2, because that's my x value from my ordered pair. Plus y, what am I replacing y with? 5, because that's my y value from the ordered pair. And now I'm working down both sides of the equation. Left-hand side, 2 plus 5, what does that give me? 7. The right-hand side, 7, is already worked out for me. Do I get a true statement plugging my ordered pair in?
Yes.
Yeah, 7 does equal 7, correct?
Yes.
So the ordered pair is a solution to my first equation. Everyone agree with that? Because it made my equation true. Does that automatically make it a solution to my system as a whole? No. Why? What was the last sentence say here on this previous slide? Do what? Yeah, it's got to be a solution for each equation. So I still have to check my second equation as well. So 2x minus 3y equals negative 11. I'm going to do the same thing. Plug in what for x? 2. Minus 3 times y. What am I plugging in for y? 5. And now I'm just working down both sides of the equation. So left-hand side, I got a little bit of work to do. We'll do multiplication first. What's 2 times 2? 4. Negative 3 times 5. What does that give me? Negative 15. The right-hand side's already worked out for me. Left-hand side, one more operation. What's 4 minus 15? Negative 11. So would 2, 5 be a solution to my second equation? Yes, because when I plug it in, it gives me a true statement. So now that I know it's a solution of both of my equations, what can I say about it being a solution or not a solution for my whole system? It is a solution because it works for both my equations. Does that make sense?
Yes.
So 2, 5 is a solution. Does everyone see how we approach that problem? Plug it in both your equations. If it makes both of them have a true statement at the end, it's a solution to your whole system. Okay? Questions on A? Letter B, negative 2, 0. And we have y equals negative 2x minus 4. Y equals x plus 4. What do I need to do? Plug it in. To which equation? Both of them. So first equation, y equals negative 2x minus 4. What am I going to replace y with? What's the y value for my ordered pair? 0. Equals negative 2 times x. What's my x value? Negative 2 minus 4. Okay, left side's already worked out for me. What would negative 2 times negative 2 give me? Positive 4. And then 4 minus 4? 0. So is this ordered pair a solution to my first equation? Yeah, it gave me a true statement, right? 0 does equal 0. Everyone agree with that? Now I've got to check my second equation. Y equals x plus 4. Once again, my y value is 0. X value is negative 2. Is there any confusion on how I'm plugging these numbers into my equations? Replace the x with your x value from the ordered pair. Replace your y with the y value from your ordered pair. From there, you're just using your order of operations to work out each side of the equation. So what's negative 2 plus 4? Positive 2. Both sides are worked out now. Does 0 equal 2? No. So, this ordered pair is a solution to my first equation, but not my second equation. Correct? So, is it a solution to the system as a whole? No, because it has to be true for both my equations. So I'd say negative 2, 0 is not a solution. Everyone okay with that? Any confusion? Can I move on? Okay. The solution of a system of linear equations is the point of intersection of the graphs of the equation. So to solve a system of equations by graphing, I just graph both lines on the same coordinate plane. Wherever they cross, wherever they intersect, that is my solution. That makes sense? Because like we said, any ordered pair on a line is a solution to that equation, right? So at the point of intersection of the two lines, that point works for both lines because it's on both lines. So that's my solution because that's the only ordered pair that works for both equations. Okay? So you may want to write these steps down to solving a system of linear equations by graphing. Step 1, graph each equation in the same coordinate plane. Step 2, estimate the point of intersection. Step 3, check the point from step 2 by substituting for x and y in each equation of the original system. Step 3 is what we just did on the previous slide. Checking your work. I'll give you a little bit of time to write these down. I can come back to these steps if I need to, but I want to move on real quick to an example. Solve the system of linear equations by graphing. Y equals negative 2x plus 5. Y equals 4x minus 1. What form are these equations in?
Slope-intercept.
Slope-intercept form. Y equals mx plus b, right? That's pretty nice because we can just use our slope and y-intercept to graph our two lines. What do you think I would need to do if they were not already in slope-intercept form? Probably put them in slope-intercept form to be able to graph them. Okay, you might see some of those on your assignment. So what does step 1 tell me to do when solving by graphing?
Graph each equation in the same coordinate plane.
Yeah, we're going to graph each equation on the same coordinate plane here. So equation 1, what's my slope?
Negative 2.
Negative 2 over
1.
1. And what's my y-intercept? 5. When I'm graphing in slope-intercept form, what's the first thing I need to graph? What? Not the slope. The y-intercept. The y-intercept is my starting point when graphing in slope-intercept form. What is a y-intercept?
That number right there.
Well, yeah, that number right there, but what does a y-intercept mean? Yeah, it's the point where my graph crosses the y-axis. So where are we crossing the y-axis for equation 1? 5. So I'm going to put a point at positive 5 on my y-axis. We okay with that? Now, using my slope to get more points, which two directions am I going and how many units if I have negative 2 over positive 1?
Down negative 2 over 1.
Down 2, right 1. Okay? 1, 2, 1. Just like that. How many points do I want you to have on your graph? As many as you can fit. Down 2, right 1. Down 2, right 1. So on and so forth. Keep doing that till you can't do it anymore. How can I get more points to the left of the y-axis?
Switch it to be negative 1 over positive.
Yep, I can flip the signs of both my denominator and numerator on my slope and go up 2, left 1. Any questions? How I got my points here? I can now draw my line. There's my graph of equation 1. Are we still good graphing linear equations? Okay, now I got to do the same thing except with equation 2. What's my slope?
4 is
4 over 1. Y-intercept?
negative 1.
-1. So I've got to graph my y-intercept first. -1. Put a point at -1 on my y-axis. Now, positive 4 over positive 1, which two directions am I going? How many units?
Up and over to the right. Up 4 and over to the right 1.
Up 4, right 1. 1, 2, 3, 4, 1. There's already a point there for me. Right? 1, 2, 3, 4, 1. I've already got that point there. 1, 2, 3, 4, 1. That's as far as I can go up and to the right. Change both signs to -4 over -1. Go down 4, left 1. 1, 2, 3, 4, 1. Okay, there's my two graphs. I've got them on the same coordinate plane. Step 1 is done. Step 2, what do I need to do? Estimate the point of intersection. So where does it look like they're intersecting each other at? 1, 3. I didn't draw my lines very straight. If I did, it would be 1, 3. This point right here, the point they both have in common. So I'm saying my solution is 1, 3. Everyone got that? For systems of equations, your answer will always be an ordered pair. You'll always have an x value and a y value most of the time. I don't want to say all the time, but most of the time. Okay? Step 2 done. I estimated my point of intersection. What does step 3 tell me to do? Check my point in both equations. That's what I did on the previous example, right? So now I've got to plug this point into both equations, make sure it works, make sure that my answer is correct. So replace my y with what? 3. Replace my x with 1. And now working down both sides of the equation. Left side's already worked out. Negative 2 times 1 gives me negative 2. And then negative 2 plus 5. 3. Does it work out for equation 1? Yes, it does. Equation 2. Y value is? 3. X value is? 1. 4 times 1? 4. 4 minus 1. Does it work out for my second equation? Yep. So I can be certain that 1, 3 is my solution. Okay? Everyone okay with that? To solve a system of equations by graphing, graph the two equations on the lines on the same graph. Wherever they're crossing each other is your solution. How many answers do I have here? How many points do they have in common?
1.
Just 1. Most of the time, you'll only have one solution for your system of equations. They'll only share 1 point most of the time. Okay? Questions on that? Okay, real quick. I want to talk about something else here real quick. Let's say my second equation was y equals negative 2x minus 3. What's my y-intercept here now? What? Negative 3. Slope? Negative 2 over 1. Down 2, right 1. Down 2, right 1. Down 2, right 1. Up 2, left 1. I've now graphed both lines on the same coordinate plane, correct? My solution of a system of linear equations is the point of intersection of the graphs of the equations. What do we notice about the graphs of these two equations? They're parallel. I could have known that beforehand by noticing what? What do I know about parallel lines? Same slope, right? So if I'm looking for the point of intersection to be my solution, but I know they're never going to intersect, what do you think my answer is here?
No.
No solution, right? Get your head up. No solution. Does that make sense?
Yeah.
Because are they ever going to have a point in common?
No.
No, so they're never going to intersect, right? So in this case, I would have no solution. Does that make sense? Okay. Let's talk about one more thing real quick, and then I'll be done. Let's say our equations were not in slope-intercept form already, so I had to get them in slope-intercept form. And when I did that, they turned out to be the same equation. So if I were to graph my second equation here, it would turn out to be the same exact line, right? Be right on top of equation 1, right? Okay, the solution is where the graphs intersect. Where are the graphs intersecting here? Do what? Everywhere, right? They intersect at every single point. They're crossing, right? Technically, their points are on top of each other. So, does this line ever stop going in either direction?
No.
No. So what would you say for the answer here?
Infinite.
Is Alana Jones in here?
What did we say?
Infinite.
Infinitely many solutions. Because every ordered pair now becomes a solution because it's crossing at every single ordered pair. Does that make sense? So, parallel lines would be no solution. If it's the same line, it'd be infinitely many solutions because it's intersecting at every single point. Okay? And it'd be impossible for me to list every single solution. Does it mean that every ordered pair is a solution? Is the ordered pair 0, 0 a solution? No. Is the ordered pair negative 10, 5 a solution? No. Just the ordered pairs that are on the line, but I still have an infinite number of those, don't I? Okay. Are there any questions? Here you go. Page 231, numbers 2 through 22 evens.
Can you go back to
Yeah, I'll go back in a second. This will be due Friday the 20th on Canvas. It's about 11 problems. You should be able to knock out a decent amount during class. Get it written down. Get the correct heading on your paper. Name, date, period, assignment, upper right-hand corner. Do we have any questions about the notes before I end the recording?